Hello, apes. Let's begin topic 1.3, aquatic biomes. Please have your guided notes nearby because you will complete them just like we do in class as we progress through the presentation. So today's lesson is about different aquatic biomes such as ponds, oceans, lakes, streams, rivers. And we'll go through each of these within our lesson. So please fill in your guided notes. Aquatic biomes are categorized by their physical characteristics. So there are three characteristics that will describe a particular biome: the salinity, which is the amount of salt, the depth, and the type of water flow. Those are the three characteristics that categorize our aquatic biomes. So please be sure to add those to your guided notes. So there are two main types of aquatic biomes. We have our freshwater biomes. Freshwater provides us with drinking water. The second type of biome is saltwater, which we call marine biomes, and those are naturally our oceans. Please fill that in. So here is a beautiful picture of a freshwater biome. And then an image of the marine saltwater biome. You have this diagram in your notes. So 97% of the water on our planet, we live on what's called the water planet, is salt water, oceans, which we cannot drink. That leaves us with 3%. 2 and 1 equals 3% of fresh water. However, of that 3%, 2% is frozen in glaciers, so we cannot access that water to drink. So this is an important number for apes, which is 1%. There is only 1% of fresh water available to us on our planet. That's a very important number for our apes curriculum, so please highlight that in your notes. So Earth, which again is the water planet, our planet is 70% water. The marine oceans comprise 97% of this water. That remains 3% of our fresh water. However, 2% is frozen in glaciers. We can't access that for drinking. So 1% fresh water is available for us to drink. Important number for our course. So some might ask, well, why can't we take the salt water from the oceans and desalinize that water, take the salt out, and provide us with fresh water? That's a great question because that is a process. Desalinization of salt water is happening in certain areas of our globe. So Please label your diagram. Again, getting to know our world map. Saudi Arabia and Libya, as well as Algeria, are using this type of method to desalinize salt water and make it into fresh water. So how does that actually happen? Well, it's a process. So let's watch a video on how this happens.
71% of our planet's surface is covered in water. 332.5 million cubic miles of it. 366 billion gallons. That's over 48 billion gallons of water for every person on Earth. But today, 1 out of 3 people don't have access to safe drinking water.
Some projections will show by 2050, more than half our population will be living in water-stressed areas. That's over 4 billion people.
These aren't just issues in developing countries, something you hear about elsewhere. These are things that are happening in our communities all the time.
Worried and angry about lead contamination
to the military in remote parts of Puerto Rico.
And that's the result of many things, but one of them is that 96.5% of that water is found in our oceans. It's saturated with salt and undrinkable. And most of the Earth's fresh water is locked away in glaciers or deep underground. Less than 1% of it is available to us.
When you dig a little bit and look under the surface, even here in the United States, we have large numbers of people that don't have access to safe, clean drinking water.
So why can't we just take all that seawater, filter out the salt, and have a nearly unlimited supply of clean, drinkable water?
Desalination, broadly, is the process of removing salts from water. It's been practiced for years. In fact, it's a natural process. It occurs when the sun heats the ocean and fresh water evaporates off and it falls again as rainfall.
If you mix salt into water, it dissolves. And if you could watch microscopically while you did that, you'd see that the water is actually breaking apart the salt into charged particles that chemically interact with the water. So salt water is a chemically new solution. It's not just water with some salt grains floating around in it. And that's why desalination is a fundamentally tricky process.
The two main types of desalination are thermal desalination and reverse osmosis. Thermal desalination is the oldest form of desalination.
It's essentially boiling water and then capturing the steam and turning that into fresh water. But in the 60s, we were able to develop reverse osmosis processes at UCLA, and these have now started to dominate the market. So one of the big chief differences between the two is reverse osmosis doesn't use heat, doesn't boil anything. You're really just pressurizing the water to a tremendous amount, and you're forcing it through a membrane where it doesn't want to go. It wants to stay with the salt, but with this high pressure, it is forced to separate from the salt. Broadly speaking, what you want to look at for desalination is, where's my fresh water coming from, and do I have enough of it? And if I don't have enough of it, do I need to augment supply? Desalination then starts to become a very attractive or interesting option.
Which is why the vast majority of desalination efforts right now are happening in places like the Middle East and North Africa, rich with fossil fuels, but also experiencing extreme water scarcity.
Just 2 countries, Saudi Arabia and UAE, they produce 1/4 of the desalination water that is produced currently on this planet.
Concerns about desalination fall broadly into 3 categories: the amount of energy required, how much it costs, and its environmental impacts.
There are some that really see it as a key solution. There are others that push back and argue that it's very energy intensive, it's very expensive, it has impacts on the marine environment, and that we should pursue alternatives first.
It requires a tremendous amount of energy to basically break up that bond between the water and the salt. Ocean water desal can be 25 times as energy intensive as other freshwater approaches.
Historically, the impediment for seawater desalination being more abundant or popular in North America has been cost. It has been cost prohibitive historically.
The Claude Lewis Carlsbad desalination plant outside of San Diego is the largest of its kind in the Western Hemisphere and has been operating since 2015, producing 50 million gallons of clean water a day. It's in San Diego County because of its dry, arid climate. The county has historically imported nearly all of its water from the Colorado River in Northern California.
In San Diego, in the Carlsbad example, they're spending twice as much for seawater desalination as they do on imported water. Now, they were looking at it and saying, well, at some point in the future, the cost will be comparable. And I think some folks pointed to the fact that, well, when that's the case, then that's probably when you should build it.
Today, desalinated water in Carlsbad costs approximately twice as much as imported water, but you're comparing apples and oranges because that imported water is coming from systems that were built a half a century ago where all the capital investment has been paid off. Standing down for 5 or 10 years hoping there's some major breakthrough in the technology is not going to materially reduce the cost of building infrastructure. That's not unique to desalined water. That's true of all public infrastructure. We have a huge deficit. We need to start building not just water, but transportation and housing now, not 5 or 10 years from now.
The Carlsbad plant is operated as a public-private partnership.
With the Carlsbad seawater desalination plant and the proposed Huntington Beach seawater desalination plant, we're proposing a public-private partnership where the plant is 100% privately financed, and then we enter into a long-term fixed-price water purchase agreement with the Public Water Agency, and essentially we're recovering our investment over time through the sale of water. There's an infrastructure deficit in the United States. There's certainly an infrastructure deficit in California, and you can't expect local, state, and federal government to pay for all of it. The private sector is going to have to invest private dollars, and I think there's a huge opportunity in water in a way that both protects the ratepayers and also allows for the investment of private capital.
Beyond the environmental costs of producing the energy needed to power these plants, another concern arises because they're not just outputting clean, desalinated water. They're also producing huge amounts of hyper-salty water called brine as a byproduct.
Seawater desalination plants that use reverse osmosis typically operate at a 50% efficiency in that if you take in 2 gallons of seawater, you're going to produce 1 gallon of fresh water and 1 gallon of hypersaline brine.
It's a fixed volume of salt that I'm trying to remove. So whether I put it in half a gallon of water or a tenth of a gallon of water, it's still going to be there and it's just going to be much more concentrated.
As desalination efforts grow, it's not clear what should be done with these huge amounts of brine. Globally, right now, we're producing over 37 billion gallons a day. Most brine is in one way or another emptied back into the ocean, but because it has a much higher salt concentration than regular seawater, it has the potential to, among other things, sink to the seafloor and wreak havoc on the plants and animals found there. In addition, because these facilities are taking in millions of gallons of seawater a day, the intake itself could destroy local marine life. But Poseidon Water, which operates the Carlsbad plant, says the regulations in California provide sufficient environmental protection.
Numerous studies have been done in California and around the world that show that level of salinity increase will not harm marine life.
And you're also providing drinking water to people in need. But a recent study published in 2018 showed that we're producing even more brine than we thought.
For every liter of desalinated water, we produce 1.5 liters of brine. In other words, overall, we are producing more brine than we produce desalinated water.
And while some places like California have robust regulations regarding brine in place, it's not clear that as a whole, the industry is taking its disposal seriously enough.
Currently, we are disposing of brine in a way which we used to dispose of industrial wastewater about 40-50 years ago.
So if desalination uses a huge amount of energy, is very expensive compared to other options, and in the end we're producing more potentially harmful brine than clean water, why do we continue to pursue it?
Desalination has its drawbacks, but one of the benefits is that it's a fairly stable and known process, particularly if you're dealing with ocean water. You can be confident that it will supply you water when you need it.
Reliability is the key. Water scarcity is a complex, difficult problem. Climate change is affecting everything and introducing growing uncertainty. Weather is variable, but if you have a desalination plant, energy, and seawater, you can reliably get clean water. But desalination undeniably uses a large amount of energy, and for some, it's just fundamentally difficult to advocate for a technology that would be adding to our ever-growing energy needs.
And I think when we start to look into these water scarce worlds, we start to think about, well, energy provides us services. It heats our homes, it lights our offices and buildings. And if we think of energy as a service that could give us water, for some context, the average person in the US uses about 100 gallons of water per day. If I were to produce that 100 gallons per day with ocean water desal, that would be the same amount of electricity consumption that my home would require over an hour. So to kind of put things in context, I think we start to think about our energy resources and where do I invest it, how important is water.
I mean, it is the most basic element of life, and people go out and they buy a venti Starbucks every day and spend more on that than they do for a month's supply of desalinated water, and they don't realize it.
It's clear that desalination alone is not going to fix the world's water problems.
Up in some places where you're just water rich, desalination probably won't make the most sense.
Poseidon Water as a company does not believe that seawater desalination is a panacea.
We can't just build 1 or 2 or 10 and really solve our water challenges.
Desalination is not the solution to water scarcity. It's one of the options to narrow the gap between water supply and demand.
But for some communities around the world, it's already making an enormous local impact.
It's currently a pretty small fraction of the water supply globally, and probably will remain so. There are, though, communities for which it is a fairly significant contribution. It can be quite important at the local level.
Desalination is one tool of many, and for it to have maximum impact, it must be implemented alongside other techniques.
Israel maybe provides a good example where they have invested quite a bit in seawater desalination, but they also made investments in efficiency such that their water use on a per person basis is far lower than we see here in California or in many parts of the United States. So they did those things first so that they aren't wasting that very expensive water. That then delayed their need to build a plant, and when they built it, they could build it a bit smaller than they would have. So there's a real cost savings there to the community.
I would almost look at it as like a safe bet. To hedge your risks, a desalination plant is your low risk option in your portfolio. Kind of expensive maybe, but it's going to deliver.
I think we do the cheaper, less environmentally damaging things first. That seawater desalination is an option. In some communities, they don't have other options. Others, though, do have other options. They can use water more efficiently, which can save water, save energy, can have less environmental impact.
And while most attention is given to seawater desalination, a similar process can be used for treating many other sources of water, like wastewater.
The volume of wastewater, if it's all collected and recycled, that is almost equivalent to 5 times the volume of water that passes through Niagara Falls each year. And if we look at the desalinated water which we produce globally on an annual basis is almost equal to half of the volume of the water that passes through Niagara Falls.
We don't want to lose sight of other sorts of desal, brackish water, which is, you can think of brackish water as it's not as salty as ocean water, but it's saltier than fresh water. It's that whole space between. And there, the energy requirements are substantially less, simply because there's less salt. So less salt, less stuff to remove, less energy.
Desalination is an important tool in the fight against water scarcity. Its reliability is becoming ever more important, but it's not a cure-all, and other techniques should always be implemented alongside it. Desalination is already vital for many water-scarce communities around the world, and as climate change continues to transform our planet, the balance between concerns about energy use and the ability to reliably get clean water is going to evolve. How exactly desalination will fit into the future of clean water is yet to be seen.
Okay, so desal water is an environmental issue we will definitely continue to follow. So let's continue with our lesson and our guided notes. So let's talk about the fresh water that is available to us. So these freshwater biomes include streams, rivers, lakes, ponds, and wetlands. Please fill these in your guided notes. And if you look through the picture here and you see these people, I'd like to draw your attention to the lady in the red on this raft, which is me. Just kidding. That's not really me. Laugh out loud. Anyway, let's turn the page and continue to complete our notes. So we'll start with our streams. Streams are categorized by two types. We have fast, which are rapids, and these have an increased oxygen flowing through the water, and that sustains trout and salmon. A slow-moving stream has less oxygen mixed throughout it, and that could support catfish. And here's our image of a stream. Rivers are typically wider and carry larger amounts of water than streams. However, it is not always clear where a stream becomes a river, so there's no set point to distinguish the two. Lakes and ponds also provide fresh water. So lakes and ponds have standing water, and some lakes or ponds are very deep, and they don't support vegetation when it gets too deep at the bottom because sunlight won't reach the bottom. And lakes are generally considered larger than ponds, but again, no clear point at which one is considered the next. So there are zones of a lake which you need to be able to identify. And we'll go through these zones, and you have a diagram to help you study these. So the littoral zone, this is the area in the lake that is very shallow. It's right along the edge of the lake, where if you were standing in front of a lake and you put your feet into the lake, that's the littoral zone. It would be shallow enough that you could stand there. The water might be up to your shins. This is where algae and plants can grow because it's shallow enough that they receive sunlight. That would be the littoral zone. The pelagic or limnetic zone, this is when you swim out into the middle of the lake, which is much deeper. So if you swam out, you would be in the middle of the lake, and this is called the limnetic zone, the open water. You might notice floating algae in a lake, and this is called phytoplankton. When we talk about the profundal zone, this is the very deep portion of the lake where sunlight does not reach. And again, you could observe these zones by looking at your diagram on your notes. Finally, the benthic zone is the muddy bottom. So B, benthic for bottom of a lake. So here is the diagram that you have in your notes as well. And again, you need to be able to identify the different zones. Turn the page, please. There are 3 trophic classifications of these lakes And you'll fill these into your notes. The three types of lakes are called oligotrophic, mesotrophic, and eutrophic. Take a moment and fill those into your notes. Oligotrophic, mesotrophic, M for middle, eutrophic. And these three terms can describe the state of an aquatic ecosystem, or in particular, a lake. So oligotrophic, if you look at the image, is a very clear, fresh, healthy looking lake. A mesotrophic lake is where you start to see sedimentation forming at the bottom. As you can see, we're starting to have more emergent plants filling the lake. It might not look as healthy as our oligotrophic lake. Finally, the eutrophic system. This lake is starting to be overgrown by emergent plants and vegetation. There's less fish, and there's more sedimentation at the bottom of this lake. Canaan Lake is a lake in our neighborhood that has undergone eutrophication. That lake had become so overrun with vegetation that man are trying to clean the lake out to try to preserve Canaan Lake so it can be returned to a healthier state known as the oligotrophic state. So right in our own neighborhood, we have a lake that has undergone eutrophication. So eutrophication is a lesson I will be teaching in class when I see you. It is a very important environmental issue, and I will be teaching that to you in class. But just know that our very own Canaan Lake has undergone eutrophication, and we'll learn more about that in class. Let's continue. Another freshwater biome is the wetlands. These are submerged by water for part of the year. They're shallow, so they support emergent plant life, vegetation. Examples of these are swamps, marshes, bogs, estuaries. And we can recognize these types of freshwater wetlands because we are surrounded by them. We live on an island, and so as you could see in blue, anything near our water, our coastlines, we have wetlands that you've probably seen all your life. And here's a nice image along the shoreline, and we call these wetlands. Our marine biomes, now remember, marine is salt water. So please fill this in. We have our salt marshes, our mangroves, the intertidal zones, coral reefs, and of course, our open oceans. These are our marine or salt water biomes. Salt marshes are very important because they are able to absorb our storm surges. Salt marshes are along the coast. They contain a lot of non-woody vegetation, no large trees generally, but rather beach grass. And these are found in temperate climates, and that's what we have along our ocean beaches. Turn the page for number 3. So these saltwater marshes we have right here on our Long Island, our very own. It's where the fresh water from a river meets with the salt water from the ocean. So again, these salt marshes, which we have right here on our very own Long Island, is where the ocean water mixes with river water. And we have a salt marsh. And again, if you could see the image and you could imagine Long Island and or Fire Island, and we have the ocean, and the ocean connects with the river. And here we would find along this our salt marshes. And these are all the different types of living things that survive in these areas. This diagram is in the right top corner of your notes. And again, this is a salt marsh showing all the different types of organisms, our beach grass, that can grow in these areas. Continuing with our outline, another marine biome is our mangrove swamps. This is marine because it is salt water, and we already know quite a lot of information about our awesome mangroves. And they're actually so beautiful to look at. Continuing with our outline, we're going to talk a moment about the intertidal zone, which sounds maybe complicated, but really is very easy to understand. So intertidal, inter means between. So between tides, we have what's called a zone, and this is the band of coastline that exists between the levels of high tide and low tide. Now, it's important to note that during high tide and low tide, there are different types of environments along the zone. During high tide, the environment is generally considered stable. However, during low tide, This is when organisms are more exposed to sunlight and higher temperatures. During low tide, the conditions become much more harsh. Many organisms have adapted nicely to an intertidal zone, and these organisms are barnacles, sponges, mussels, algae, crabs, and sea stars. But I like to show an image to help explain on the next page exactly how an intertidal zone might look like. So, turn to the next page, please. So if you imagine along the coast, if you imagine our very own Long Island, and along the coast, we might see our tides rising to high tide, and then our tides recede to low tide. So the levels of water will rise. So at high tide, the coast is covered in water. And when it's covered in water in high tide, these creatures are feeling much more stable. They are not exposed to the sunlight during high tide. They're underwater. However, when the tide recedes and the water is at low tide at this level, you can then imagine these particular organisms are now exposed to the sunlight, and now they have experiencing higher temperatures. They are now in a more harsh condition and much more vulnerable. So this is called the intertidal zones, meaning between tides, between high tide and low tide. There is a place called the Bay of Fundy. This is found in Nova Scotia. I'd like you to locate Nova Scotia on your world map when you get a moment. You might want to Google that. This is one of the largest intertidal zones on our planet. So let's see if I can get the video to run. Here it is, the intertidal zone at the Bay of Fundy. There is our intertidal zone, our coastline.
It is forever fluctuating, and its shoreline evolves with each passing wave. As the water in the Bay of Fundy ebbs and flows, it creates a phenomenon that occurs nowhere else on the planet. Located on the east coast of Canada, and resting on the coastlines of the provinces of New Brunswick and Nova Scotia, and the American state of Maine, the Bay of Fundy stretches 180 miles long, and the mouth of the bay is 62 miles wide, with its depth ranging between 400 and 700 feet. The tides of the Bay of Fundy are so dramatic that they are considered the highest tides in the world. There are a few reasons why this area of New Brunswick experiences the highest tides. One major reason is its funnel formation. As the gravitational forces of the sun and moon combine to create a continuum of tidal action all over the world, this unique shape of the bay allows for water to flow into a narrow point, leaving it no place to go but up. So how much water actually flows into this area? Well, how about 200 billion tons each day?
Oceanographers calculate that equals the discharge of every single freshwater river on planet Earth in a day. And the one I like best, if you bulldoze New Brunswick, Nova Scotia, and PEI flat, and you allowed the water to accumulate from those two tides, you'd actually be standing thigh deep in water anywhere in maritime Canada. Unbelievable.
So as you can see, the intertidal zone occurs at the Bay of Fundy. And I have another video showing this time lapse. Again, the Bay of Fundy. Okay, let's continue to coral reefs. Coral reefs, you should have done research about the coral reefs for your September assignment. There is an amazing documentary I invite you to watch. It's called Chasing Coral, and it's very, very inspirational documentary. And I invite you to watch that when you get a moment. We'll talk more about coral reefs in class. And here's an image of coral reefs. And again, I'm going to spend because they are a very, very important ecosystem to our planet. And here are the notes, which are included in your outline. Hopefully you did some research and you're able to understand a little bit more about coral bleaching, which is something happening on our planet. And here's some information about coral bleaching. We'll talk more about that in class. Finally, we'll discuss the open ocean, marine biome. The open ocean, if you imagine, sunlight cannot reach the bottom. Sunlight can only reach about 650 feet. So after that, it's the abyssal zone. This is where there is no photosynthesis occurring. The abyssal zone is where it's very deep in the ocean and we have no photosynthesis occurring. The zones of the ocean are divided into 3 zones. We have the photic zone, which I'd like you to fill in on your diagram at the bottom of page 6. The photic zone is the upper layer, and that's where sun can reach and photosynthesis can occur. So the photic zone, please fill in your diagram, is the top layer. The abyssal zone, which is aphotic, this is where there is no photosynthesis occurring because that is where there is no more sunlight. And then the very, very bottom on your diagram, please fill in the benthic zone, which is the B for bottom. Now, as you look at the diagram on your notes, you'll notice that as you go from the photic zone down into the benthic zone, we have light decreasing, but pressure increasing. Pressure increases the further you go down to the ocean floor. Please turn to the next page of your notes and please fill in and label the zones of the lake from the pages before. You should be able to identify these zones. And also, you should be able to label the 3 lakes and their trophic level. So if you recall from a few pages before, you must be able to identify an oligotrophic, a mesotrophic, and a eutrophic lake. So oligotrophic, nice and clean. Our mesotrophic, we're starting to see some emergent vegetation, sedimentation forming at the bottom. And then our eutrophic lake, where we see the lake is really being overgrown. I'm going to spend time in class talking about the process of eutrophication once again. This is where I'm going to end the lesson. This ends topic 1.3. Thank you so much, and I will see you soon. Bye, folks.